Hi guys, that's Monday, normal. It'll look a lot like what we've had. Like I've told you, we'll have 45 to 48 questions. I think it's sitting right around 46 or 47, so it'll be right around there. I'm not completely done with the test. But the way for you to study is you to go through the tests and work through the 4 tests that we've had. And what I do is I go through and I pick 12 questions from each exam. So they all add up to 48. And then I'll lose some of those as I go along. But then I look at each question and I say, okay, what is this question asking? And what's maybe another way that I can ask it? And so, like for example, there is a question like number 2. But I don't ask for the area of a slice of bread. I ask for the area of something else. And it might be in square centimeters. It might be in square meters, square millimeters. So you need to know those measurements and be able to apply them to something. Some of the calculation problems, I might just change the numbers. Like for example, I might give you this problem, but just give you different numbers on the triangle and ask you to calculate what is x or what is theta. On other problems, I might change them in what I ask for. So for example, number 10, which is a kinematics problem, I could go and give you a question about what is her speed after so many seconds, or what kind of distance has she traveled in so many seconds. So as you study, you should do a similar thing where you go through each question and you ask yourself, okay, what type of question is this and what is it asking? And what are some other ways that I could think about this? And that's where it might be useful for you if, for example, you're not very good at kinematics problems, that you go back and you review your notes. You go back and review other exams, or maybe even go back and look at the OpenStax for those, although that's probably less useful for you to revisit the OpenStax. Looking at old exams and reviewing your notes and the homework in the book itself, in the workbook, would be helpful for you. Okay? Particular questions that you want to deal with today? Yeah, William?
For example, regarding like what are the instances where force of weight equals normal force?
What are the instances where force of weight equals normal force?
Yeah.
Well, like for example, number 12. I assume that's the one you're talking about. I think there was another one.
Yeah.
Yeah, number 12 was a work problem, but it had to do with normal force too, because you had to figure out what was the friction. All right, so what is the work done by the man on the block? Actually, no. No, this one wasn't. No, you didn't have to know the normal force to this one at all, because all you were finding is the work, which is just 45 times cosine of 28 times the distance that it travels. But if you wanted to know the normal force in this case, there was another problem. What was that? Oh, that's exam 3. You said exam 2, right?
Yeah.
Yeah, like this one. So this one, what is the normal force on the block? Good question. I could ask you any series of things. Like I could ask you, what is the friction? I could ask you, like the previous problem, the work problem, I could combine 2 problems because those 2 problems are very similar, that I could take this question and ask, what is the work done by friction? Or, yeah, any number of ways that I could change this. But the point is that you need to be able to work a problem that has 2D forces. It would look very similar to this. And be able to figure out what is the acceleration, what is the work done by those forces. In this case, when you're looking for the normal force, well, we'll start by drawing our axes and then labeling the forces. We have a 40 Newton force that's at 30 degrees from the axis. We have the weight, Fw, and then we have the normal force, Fn. And in this case, we also have a kinetic frictional force. And then we will go through those steps. These steps will always be the same. You'll follow the same steps on the test. It might just be a slightly different context. And the steps are to resolve this vector into its components, right? It's x and y components. 40 cosine 30 down here, 40 sine 30 right here. And then you would apply Newton's second law, where you do the sum of the forces equals ma. We could step through that here, where I would have my forces would be Fn, 40 sine of 30, and then down here at Fw, but Fw is 110 newtons. That's 11 times 10. And then I'd solve this for the normal force. I would say 40 sine 30 plus Fn equals 110. And so Fn is 110 minus 40 sine 30. It's 90 newtons. Sine of 30 is a half, right? So, if I were to ask this on another test, I could ask, as I said, different things. Like, for example, how would I figure out what is the work done on this object? That could be an okay question because this question comes up again in a later test. William?
So in this scenario, force of weight equals a normal force, right?
No. No, it doesn't because the weight is 110 newtons, but the normal force is 90 newtons. And we have to go through this process in order to figure out what is the normal force. The normal force is less because the guy's pulling up on the object. It's less than the weight by 40 sine 30. It's less by that amount.
So what are the instances that normal force equals force of weight?
Where it's on a horizontal surface and where there are no other vertical forces. Okay? Now, what if I were to say, what is the work done on this object? Would you know how to do that? Well, let's go through that problem, okay? Because that's a good way of thinking about this is a problem and how can I change it. If I wanted to know what is the work done on this object, what is work equal to? Well, there are two forces doing work, right? There's the force that this guy is applying. So I have a F cosine 30. And then I also have another force that's in this direction, Fk. The forces that are acting here, these vertical forces, doing no work because there's no displacement in the y direction. But the forces, I have two amounts of work. The work done by, I'll call it Wf, is going to be F cosine 30 times the distance. I don't give you a distance in this problem, but on exam 3 there was a very similar problem that had a distance. Let's just say it's 2 meters. Y'all following me what I'm doing here? I'm just creating another problem that's similar to this that requires a similar process, but similar but different. So I'd say F cosine 30 times D. And so the work done by that force would be 40 times cosine 30. That's 35 times 2, 35 newtons times 2 meters. That's equal to 70 newton meters, or 70 joules. And then there's also the work done by the frictional force. And the frictional force, I have to figure out what the frictional force is. Fk, I know that mu is 0.1 times the normal force, which I found to be 90. And so Fk is 9 newtons. And so the work done by friction is going to be negative because the friction is opposite the direction of the displacement times Fk, which is 9 newtons, times 2 meters, are negative 18 newton meters. And so if I want to know, I could ask several questions. I could ask, what is the work done by the force, by the guy? What is the work done by the frictional force? Or I could ask, what is the total work being done? And the total work being done would be 70 minus 18, which is 52, or in this case, 50 newton meters, or 50 joules. That's a good example of how I could take a problem and make it different. You need to be prepared to do problems like that because you'll have 1, 2, maybe 3 two-dimensional problems. You'll have at least 2. I think there might be 3. Okay? So make sure as you go through, make sure that you can do those. Those tend to be some of the more difficult problems, right? The 2D problems, you got to deal with the vectors, you got to deal with the resolving vectors. Y'all would be okay with that right now? I gave you the test. Make sure you review those 2D problems. There are several in the exams. William?
So that's exam 2.
This is exam 2, right? All from this semester.
What was done for the work by friction?
What was done for the work by friction?
Yeah.
The work done by friction, oh, I'm sorry, I miswrote this. It should be WF. Oh, no, I'm sorry. That was right. The work done by friction is right here. It's just the frictional force, which is 9 newtons, right there times the displacement, the distance that it travels. Any other particular questions from the exams? I know they all must have particular questions.
Problems involved force. What are the steps involved for like?
Okay.
So
They're the same steps that we've done here. You label the forces on a free body diagram. You resolve the forces into their x and y components. That's what I did here. If necessary, that's not always necessary, you know. Then you apply Newton's second law, where you say the sum of the forces is equal to ma. And that's what we did here, where I said this minus this is equal to the mass times acceleration. In this case, the acceleration was 0, so it looked like that. We follow that same procedure every time. Label the forces, put them on a coordinate system, apply Newton's second law, and then solve the equations.
So 9 newtons came from where?
9 newtons?
90.
Oh, 90 newtons is the normal force. This is how we got the normal force. You want me to skim through and y'all can holler out when you see one? Is it? Yeah, go ahead.
So, correct me if I'm wrong, I don't think we have the finals from the previous exam. So, do you want us to just go look over the tests from this? And if we can, like, work off...
I don't know how useful the finals from the previous years would be. I'll certainly provide them to you if you want them. Or if you just want to
So,
practice
like,
them.
Yeah, just for more practice.
Yeah, they're not new problems. You won't see new problems in this finals because what I've done is usually when I have a final is I'll use those. So like the questions that you've been seeing on OpenStax, the ones that I've written, were from last year's final. Alright, so those are new questions, but now you've seen them before. But I'm willing to provide them. It might help you to practice, just sort of get a feel. You want me to do that? I'll give you all my final exams. I'll just post them on Moodle. They don't have solutions to them, but you'll have the answer correct. All right, let me make a note for myself. You had another question?
Yeah, sorry.
This is your last one.
Oh, I hit my limit? So like, if we could say, rework all the exams from this semester, no problem, you think we'd do good? Like, I'm just trying to figure out how to just step.
No, I don't want you to get in that trap where you think that, oh, if I can rework every exam from this semester, then I'll be okay. All right. Because I want you to understand the context and the content of each question. I'm not going to write a completely different force problem, for example.
Go through all of them and understand all.
Yes. If you can do that, you're
I'm
fine.
not gonna like throw something new at me. Okay.
Nothing new. You'll see no material that wasn't on the first 4 exams.
Okay.
But you will see them. In fact, most of the questions, practically all the questions, you'll say, oh, that's from exam 2, that was that problem, but I see how he's changed it.
So say like on chapter, like, I'm just totally making things up. Chapter 5, you forgot to ask.
I am too.
Like on this exam, exam for chapter 5, you didn't ask about this one thing that was in the notes.
Right. That won't be on the final. It has to be on the 4 exams to make it onto the final. Okay, there will be no material. And you won't see everything, right? I only pulled 12 questions from each test. So, I don't know, for example, I don't know this, but you might not see the ice problem. I might have put the ice problem on there. I don't remember. You remember the ice problem? I know. Wasn't it terrible? But you might see it. I was just pulling one out. But, okay. You should know how to do every question. All 100 or so, 104 questions. 14 questions, John?
No, is it just like working out or are you gonna have concept?
Yeah, there'll be a mix of concept and calculation. Yeah, same concept questions. In fact, but, so for example, let me show you how I changed those. William, I saw your hand up and I'll get you in just a second. Like, for example, number 28. I would do this, but of course I'd write a whole new batch of equations. They would all be different from these equations. This is where you had to write out the equations for the inclined plane. And like number 18, where you had to assess whether or not these statements were true, whole new batch of questions, or a whole new batch of statements that may or may not be true.
So like, so you know how the exam, you test on like the same stuff every year, but you word it different. If I could go and work those two and like.
Yeah, but there'll be different questions too, right? Like every question is new every year. Sometimes, I'll rewrite a question and it turns out that it's the same as a previous question. But yeah, I think reviewing older exams is also useful, especially if it's a area that you're weaker in. But if you come to a question you're like, man, I got kinematics, then don't spend any more time on it. Move on to 2D forces or work or whatever it is. William?
So for questions like number 18, it's just going to be the same statement, just written in a different way.
No. No, what I said is that I could take this question, I think I don't remember if this was on there or not. I think that it was. But I could take it and I could say, well, I just get rid of these and just write entirely new statements. Like I could say, what would I say? What's different on here? I don't know. I could say the frictional force is dependent upon the mass of the object. Oh, that's on there. I can say the frictional force gets to be increases if the speed of the object increases, right? That's not a true statement. The kinetic frictional force stays constant. So it could be a whole new batch of questions, but it'd still be about an object with a frictional force on an inclined plane.
And that's a scenario. What would be the study material?
What would be the study material?
Yeah.
As I said, the 4 exams, the material will come from those 4 exams, but if you have a topic in those 4 exams, then you should review your notes, review other old exams. All right? Other questions? You want me to skim through? William?
For exam, I think it was number 3, I think. And it had something to do with.
You're going to see one of these questions. Make sure you can do these, right? Conservation of energy.
Conservation of energy, please.
Like something to do with how to set up the initial and final kinetic and potential energies.
Okay, that's like number 3. Let's do this. And listen, the way I would change number 3, and I'm pretty sure it's on the test, is that I could give you the same figure, but say, what if I gave it a velocity here? Then the way you'd work it would be a little bit different, right? Because I would have both kinetic and potential. And here I was asking for C. What if I asked it at B? And it would be a different way of working the problem. The same technique and method, but the details would be different. Well, let's just go through this. So let's say, let's just say I give it a velocity. Let's say that the velocity here is 1 meter per second, not at rest, as it says, at point A. And in that case, I would say at point A, it has a kinetic energy and it has a potential energy. And at point C, it has a kinetic energy and a potential energy. Right? And that wasn't true in the original question. I would say 1/2 m 1 meter per second squared plus mg times 5 is equal to 1/2 m times v squared, that's what I'm looking for, plus mg times 2. And then I get rid of my masses because they all cancel out. Remember, that's not true with springs when I'm doing those spring questions. And I have 1/2 plus 50, 50 point.
Excuse me.
Yeah.
Slow down a bit, please. Can you keep off?
Okay. I'll stop here in just a second. So anyway, you solve for v at that point.
So wait, I was just trying. So first you put everything in place. So you found the energy of A, which is 1/2 of mass times this times velocity plus the potential energy of A, which is again the mass times gravity
Times h, mgh.
Right.
All right. So you need to be prepared for those types of questions. You understand how I change up these questions? You're following me? Right. What else? Yep.
Why did you label it as A and C?
Because at point A and at point C. What else? Y'all can sort of solve the algebra on your own later. That's not, I mean, it's important, but I think y'all know how to do that, right? Solve for V.
Okay.
Um,
Okay.
yeah,
Get 5, please.
5. Oh, yeah. So, what this object has done is it has lost some energy. And the reason it's lost energy, it has had a change in kinetic energy. Right? It went from 6 meters per second to 4 meters per second. The reason it lost kinetic energy is because the frictional force has done work on that object. Change in energy is equal to work. That's the change in energy, work energy theorem is equal to work. And the change in kinetic energy is 1/2 m times Vs squared. That's 6 meters per second squared minus 1/2 m times 4 meters per second squared. I think this was an OpenStax question when we gave it initially. See, this is my change in kinetic energy. Final kinetic energy, initial kinetic energy. Is that right? Actually, no, it's the other way around. The 6 should go over there. So this should be 4, and this should be 6. This is kinetic energy final, kinetic energy initial. With me, folks? That's equal to the frictional force. Remember, the frictional force is mu times the normal force, and the normal force is m times g times the distance, which in the distance here, I'm going to put that number in, is 2 meters. Let me write above this sort of what we did. I said that this is the frictional force times distance. That is mu times the normal force times the distance. That's mu mg times the distance. I made several steps there in writing that. This is my frictional force, and this is my normal force, mg.
FND equals mu mgd.
Right. Notice I can get rid of my masses. They just go away. I can cancel them out because they're in every term. And then the only unknown that I have is mu. So I can solve that for mu. All right? It's a good question because it incorporates friction. It incorporates the work energy theorem. It incorporates our normal force. I love it when our questions have lots of different topics. So that, you have to incorporate a lot of different ideas. And I'm not saying this question's on the test, but it's the kind of question that I would like to pick because it incorporates different ideas. Same with that problem where the guy was pulling the thing, the block. I like that question. I get it on 2 tests, so you'll probably see something like it on the exam on Monday. I like those questions that incorporate different ideas. Those are more complex, more complicated. Of course, you'll have the simpler questions too. I don't use all difficult questions. I'll pull some what I hope are gimme questions. And a few questions will be exactly the same. So hopefully you'll just say, oh, yeah, I remember that. Like some of the conceptual questions, I just kept the same. But not very many, only a couple, 2 or 3 maybe.
What about a problem like setting initial kinetic energy and initial potential energy is equal to either final kinetic energy or potential kinetic energy?
Right, number 3? Right, number 3?
2.
Well, number 2 is the same. So, I mean, number 2 and 3 were
Okay.
practically identical. I know, but we can come back to that if we have more time at the end, because these are you work these the same way. What about other questions there? Y'all feeling nervous? A little bit nervous?
Sort of, yeah.
Yeah, that's okay to feel a little nervous.
there's still little questions, and that if I only get a few wrong, it just puts everything in jeopardy.
Well, there are 48 questions, 47 questions. That's quite a lot, actually. I mean, that's sort of pushing the limit of what you can work in 2 hours. Though, you know, some people will be done in an hour and a half, hour and 15 minutes. It takes me about 30 to 40 minutes, but you know, I write the darn thing, so.
That's what you do for a living.
Yeah, I know exactly what to do, but you know, if you know it cold, you should be able to work it in an hour. But nobody really knows it that cold. Let's just sort of skim through, okay? Oh, look, number 12, that's like the problem I worked before. It's very similar. Again, look for these problems that incorporate many different ideas. I think there are a couple unit questions. What are the units? Yeah, John. Yeah. Honestly, the ice problem, I don't remember if I gave it to you, but I would probably just give it to you exactly the same, just change the numbers on it. The ice problem, where is it? What number was it? Oh, no? Oh, number 19. I don't remember if I put it on the test, first of all, but let's spend a little time on it. So I have this block of ice. I want to submerge it. However, I know that it has a buoyant force. I know that it has a weight. And then I know, in addition, that I will have to apply an additional force. And that's the force that I want to know. Because I know a piece of ice will normally float up at the top with part of it sticking up above the top of the surface. And the reason that is that the density of ice is equal to 917 kilograms per cubic meter. Okay? So our first thing is we need to know what is the buoyant force. And it's the density of water, not of ice, times the volume of the block times g. But I don't know the volume of the block. However, I know the mass of the block, and I know the density of the block. And so I have to do this little side deal over here, where I say, well, density is mass over volume. So volume is mass over density. And the tricky part on this is keeping all your densities straight, because I got two densities floating around. I got the density of water and the density of ice, but in this case, I need to know the density of ice, because I want to know the volume of the ice, not of the water. And so it's going to be 0.5 over 917. And that's 5.4 times 10 to the minus 4. 5.5 times 10 to the minus. Which I'm going to keep 3 sig figs. I don't think it matters, but I'll just keep 3 sig figs for now. So that's my volume. And then that's the volume of the block. So I take that and I put it right there. And then I can find that buoyant force. Density of water is 1,000 times 5.45 times 10 to the minus 4 times g, which is 10. And I get 5.5 newtons. So, we're almost done. The buoyant force is 5.5 newtons. The weight is 5 newtons. So what additional force do you have to apply? You have to apply 0.5 newtons. So B was the right answer. I like that problem because it incorporates the definition of density and buoyant force in the same problem. It was on the exam, but it might have got cut because it's sort of one of the more complicated problems that we did. And I went through and I was trying to make it a little bit easier. I know I cut some of the other more difficult problems. But it was on my first cut. That gives you an idea. But I don't remember. It might have missed the second cut. Okay.
And can you do on top? I think it was number 5 for example.
On this exam?
Yeah.
Sure. Look, you're going to have to do a torques problem. Make sure you can do this, where you can find the net torque, find the moment of inertia, and find the angular acceleration. We had 2 or 3 or maybe even 4 questions. So make sure that you can do problems like 18 and 16 and 17. Number 5, the Ferris wheel. Like the ice block, this was one that made my first cut onto the exam. But, you know, I get more than I need in the first cut, so it might have got cut out. But on the Ferris wheel, looks like this. This was at the lowest point. I have 2 forces acting on them. I have the normal force, and I have the weight. And I also know that on the Ferris wheel, I'm accelerating. And so I'm accelerating in this direction, always towards the center. Look, this is exactly the same as the elevator problem. If my elevator is accelerating upward, then that's like this situation. If my elevator is accelerating downward, then it's like at the top of the Ferris wheel where your acceleration is in the downward direction. You remember the elevator problem? Okay, you could also see that. That was on exam 2. But the way I work it is exactly the same. I say the sum of the forces is equal to MA. The sum of the forces is Fn minus Fw. And this is where it gets a little different. MA is not A, it's omega squared R. That's my centripetal acceleration. Or A can be V squared over R, omega squared R. But I use this omega squared because that's what I was given in the problem. Remember, you can go back and forth between omega and V if you have, if you have the radius. I'm looking for Fn. So it is Fw plus M omega squared R. This person is 100 kilograms, so it's 1,000 newtons plus 100 kilograms, 0.1 squared, that's omega, times the radius, which is 20. And so that was 1,020. A was the right answer. Remember, I could have gone through and looked, though. I know that at the bottom, my normal force is more than the weight, so I would have gotten rid of B, C, and D, and so I'm left with A and E. That's kind of a big like a big addition to your normal force. Like you feel a lot heavier with E than you do, and you just don't feel that way on a Ferris wheel. So E, I probably could have reasoned E away, but you really need to go through the calculation. The way you change this, if I gave you this problem, most likely the way I change it is to be not the lowest point, but the highest point. And you would work it exactly the same way, except at the highest point, the only thing that would change is that this acceleration would be negative. And so this would be negative, and so this would be negative, and so the answer would be 980. The answer would have been D if it was at the highest point, not
it'd be minus.
Right, because at the highest point, your acceleration is down. The acceleration is always towards the center. Right, centripetal, center seeking, it's always towards the center. All right. Again, it made the first cut. I don't know if it's on the exam. It might have got cut again. As I was trying to get rid of some more difficult problems in this one. Yeah.
Do you think four likely to go on exam? 4 on this?
Huh?
Probably on exam.
Number 4?
Yeah.
I don't remember. We can look at number 4. A lot of people missed number 4. I was kind of disappointed. Like, we worked it in class. It was on OpenStax. I was hoping it was going to be a gimme question. Because you remember with this, I have my road here. I have a car on that road. I know that my frictional force, as this car goes around, my frictional force is in that direction, right? Because if I didn't have the frictional force, the car would just go straight off the road. The frictional force causes it to move in that circular path. And so my frictional force acts as my centripetal force. It is the centripetal force. The frictional force is mu times the normal force Notice my masses cancel. That's good because the maximum speed on a road is not set by the mass of the car. The same is true for a Hyundai or a Hummer. And here I was looking for V. It's just the square root of mu GR. I forget, I think it was 19 for this one. The square root of 0.7 times 10 times 50. Yeah. Absolutely. I'm pretty sure that you do have some I'm pretty sure that I put vectors on. That's sort of foundational. Both graphical and numerical. That was exam 2, right? Oh yeah. So, yeah, let's look at 24 first. William, you had a question about this?
The differences are like equations for static and kinetic.
Okay, we'll get back to that in a second. So I want to know the sum of these two vectors. And you know, the way I'd change this is I'll give you different values for the vectors, and I could ask for the direction, or I could ask for the magnitude of the resultant. Pretty sure this is on there, that you'd be able to add two vectors. So I like to draw a picture first. It helps me to think about the answers. In fact, you might be able to pick out the answer just by looking at the picture. 3 units at 30 degrees from the positive x-axis, where this angle is 30, and then 4 units along the negative x-axis. So, yeah, man, look, is that right? Oh, no, that wasn't right. Along the negative x-axis. It was in this direction. 4, 3. I know that this can't be the answer, E, because that would put the resultant here. And I know that it has to lie somewhere between 30 and 180. I can probably get rid of A, C, and D. Does anybody know what the answer is?
B.
It's probably B, just looking at this. But I'm not certain of that, so I probably want to work through it. But if I get B at the end, I say, oh, well, that sort of fits with what I think it should be. The answer is probably B. First thing I would do is I would resolve that vector that's not on axis. So I have my 4 right here. This is 3 cosine 30. That's 2.6, right? 3 cosine 30 is the x component. And then here, I have 3 sine 30. That's 1.5. 3 sine 30 equals 1.5. And then I add up those vectors that are on the same axis. So over here, I have 4 minus 2.6. That's 1.4. Here I have 1.5. And then I find out what is the angle between those. I like to redraw them. 1.4, 1.5. This is my resultant vector. I want to know what is this angle.
Are you going before again, sir?
I said the difference in these two numbers. 4 minus, or 2.6 minus 4 is negative 1.4. So I draw it on the negative x-axis. I just take the difference in those two. And then I'm looking for the angle, so I say the inverse tan of opposite over adjacent, 1.5 over 1.4. $47 degrees. Oh shoot, that's not on there. Right. Yeah, so I was being kind of nice by not putting 47 as an option, because many of you would have just stopped right there. But I would realize then that, oh, I'm looking for, if my resultant is right here, I'm looking for this angle. So it's going to be 180 minus 47, which is 133 degrees from the positive x-axis. So B is the right answer. Which fits with what I think the answer should be, right? Like, it seems like the reasonable answer for that. I could also ask you what's the magnitude of the vector. Well, I'd say the square root of 1.5 squared plus the square root of 1.4 squared. Pretty sure that's on there. I'm pretty sure this other problem is on there too, where I ask you what is the sum or the difference of the vectors. You need to know how to do sums and differences. If I'm doing A minus B, since B is negated, that just means I flip the direction for B. And so I would have B right here, and then the resultant would start at the beginning and go to the end. So the answer here would be C, the vector that looks like that resultant vector. Ross?
Okay, I was trying to ask, like, how you put them into order, like, how you're supposed to.
Yeah, you write the
point
first vector first, and then the second vector, starting at the tip of the first vector. You get the tail of the second vector, and in this case, since B was negated, I flipped the direction of B. I just changed the direction of B.
How you know what? And why isn't the tail of the third one attached to the head of the second one?
Because I always like to think of it in terms of displacement. If I start right here and I walk along this direction and then along this direction, this is my final point. I always start at the beginning and then I walk along there until I get to the end. I always start at the beginning and go to the end with my vectors. It's like a displacement vector. And I can get there either by going this way or by going this way. Those are equal to one another. A minus B is equal to this vector. They're the same. All right? They're the same vectors. Ooh.
So, number 24 we don't, the answer was like 133 from the positive x. If you had 47 degrees from the negative x-axis.
That would be correct too, yeah.
I just wanted to check.
Yeah, and that's a good point, that I could write it like that. So,
That's one we
yeah, on this question, drawing the picture really helps. Some of you don't draw pictures, I know, but it always helps me. And, you know, this exam, you have a little bit more time. Just take a big deep breath and just take a little time to draw those pictures. Yeah, you have more time per question. And in fact, really, I really give you 2.5 hours with the assessment sort of built in there. And the assessment doesn't take half an hour. So really, it's really a little more than 2 hours you get. And we have the last exam of the day, right? We're at 1.
Yes.
I will not give you unlimited time, but I'll give you 2.5 hours for the whole kit and caboodle. If you have to take this assessment at the end, it's 20 questions. Study for the final. You'll study for the assessment. It's worth 5 extra credit points, some percentage. Usually, students get 2 or 3 or 4 points out of that. It's worth it. Yeah, I want you to do as well as you can. It helps us. How are the classes doing from year to year? It's the same assessment that students have taken. And it doesn't impact your grade that much. And it only helps. It doesn't hurt. All right.
So that's credit points.
You get an extra little assessment at the end. It's 20 questions, 15 or 20. Other questions?
As for previous tests, for test 1 and 2, there was no formulas given back for those tests. I'm just curious.
That's correct.
I'm just curious if you're providing a formula.
You'll get what you got on the previous exams, and that doesn't include equations for test 1 and test 2, but there aren't that many equations for chapters 1 and 2, frankly, or 3. There's just the 2 kinematics equations, which really you have on the equation sheet. They're just written in terms of rotational motion, and there's F equals ma. That's it.
And those equations are velocity equals b non plus
Plus at, and the x equation, but that's on the equation sheet, but just for theta omega, not v and x. I think y'all know those equations. Y'all certainly know F equals ma. And the only other thing from those chapters are the trig functions, but again, I think that's something that y'all know, right? It's something that y'all know? Yeah? Feeling better about it than when you walked in?
Sort of. Maybe.
All right.
Maybe
Don't.
not.
Are we done?
I'm not too certain.
Okay, well, give me just a minute. Don't leave yet, because I need to